something appeared in the raw data that nobody had predicted. Not a glitch, not an artifact, not a processing error. Something real, sitting inside the unprocessed frames coming off the world's largest digital camera, waiting to be understood. And the longer astronomers looked at it, the less it resembled anything already in the textbooks. That is where this story begins. Not with a press release, not with a polished announcement, but with raw pixels, with data so fresh it was still warm from the mountain. The Vera Rubin Observatory had not yet begun its official scientific survey when its camera started returning images that did not match expectations. The legacy survey of space and time, the grand 10-year program the observatory was built to execute, had not formally opened. What was flowing down from Cerro Pachon in the months between mid-2025 and early 2026 was commissioning data. Test exposures, frames taken to calibrate mirrors, verify focus, check color filter alignment, stress test pipelines. Engineering runs, in the formal language of the project. The kind of data that typically gets filed away internally, examined for instrument performance and never seen by the outside world. Except this data was different, and the people examining it started finding things that were not on the checklist. To understand what they found, it helps to understand exactly what kind of light this instrument collects and how. The LSST camera mounted at the Rubin Observatory is not simply a bigger version of existing technology. It is a different category of instrument. Its focal plane, a mosaic of 189 charge-coupled device sensors arranged into 21 modular rafts, captures 3.2 gigapixels per exposure. Each exposure covers 9.6 square degrees of sky, roughly 45 times the area of the full moon as seen from Earth. The camera cycles through 6 filters spanning ultraviolet, the full visible spectrum, and into the near-infrared, meaning the same patch of sky can be sampled in multiple wavelengths across a single night. The telescope itself can swing to a new target and begin a fresh exposure in approximately 5 seconds. And every clear night, the mountain generates around 20 terabytes of raw data. That figure, 20 terabytes per night, is not a storage specification. It is a description of the sheer volume of information being extracted from the sky during what was still, technically, a test phase. When the team released the first batch of public images in June 2025, the world focused on the obvious headline: the Trifid and Lagoon nebulae rendered in extraordinary detail. The Virgo cluster, in a single composite frame, containing something close to 10 million galaxies. These were the images designed for public communication, and they performed that function magnificently. But sitting inside the same 10-hour observing window that produced those headline frames was something else entirely. Something the release events did not fully surface. Something the raw frames had already recorded before anyone had decided what to call it. The first sign came from the transient alert pipeline. Rubin's data processing system is engineered to compare each new exposure against a reference image of the same patch of sky, then flag everything that has changed. An object that brightens suddenly, a star that fades, a point of light that appears where none existed before, a source that moves. The system issues these flags as automated alerts, broadcasting them in near real time to observatories worldwide. During commissioning, the alert rates were already running at a scale that previous surveys had never approached. But inside those alerts, mixed into the stream of known variable stars and cataloged moving bodies and expected transient events, were sources that did not match any category cleanly. Objects whose behavior, whose brightness profile over time, whose color signature across multiple filters, placed them in territory that existing classification frameworks had not been built to handle. The technical term astronomers use for this is outlier behavior. A source is an outlier when its measured properties cannot be reconciled with any of the known populations of objects that share its apparent location in the sky. Every survey produces some outliers. Detector artifacts produce them. Cosmic rays hitting the sensor produce them. Unusual atmospheric conditions can produce them. The pipelines for modern surveys are sophisticated enough to eliminate most of these instrumental false positives before the alerts go out. What remained after that filtering were sources that were genuinely anomalous in their physical behavior, not errors. Events. Some of them were rapid transients, objects that brightened and faded on timescales of hours rather than days. Conventional supernovae take weeks to rise and weeks more to decline. Kilonovae, the explosions that occur when two neutron stars merge, are faster but carry a specific color evolution as heavy elements are synthesized in the expanding debris cloud. These new sources were different again. Their timescales were compressed in ways that did not fit established templates. A subset of them showed brightness changes on scales of minutes to hours, with color behavior across Rubin's filter set that suggested they were not simply background objects caught at an unusual phase. They were doing something. The question was what? Astronomers working on the commissioning data had a name already coined in the literature for this class of behavior: fast blue optical transients, sometimes abbreviated FBOTs, had been identified in previous surveys but only rarely, partly because finding them requires being able to image the same patch of sky repeatedly across a single night, with enough sensitivity to catch the rise and fall of a very short brightness spike. Most asteroid surveys are not designed for this. Most transient surveys lack the sensitivity. Rubin, with its 8.4-meter primary mirror and its 3.2 gigapixel camera cycling through the sky every few seconds of swing time, is precisely the kind of instrument that could catch them in numbers large enough to begin building a statistical picture. The raw frames from the commissioning period contained what appeared to be multiple candidates consistent with this category, at distances placing them in other galaxies, identified not across months of searching, but across a few weeks of engineering observation. If confirmed at the rates the commissioning data suggested, Rubin would be finding fast blue optical transients at a cadence orders of magnitude higher than any previous survey. The implications of that density are not cosmetic. FBOTs remain one of the most poorly understood categories of energetic astrophysical events in the modern era. Their power output is enormous, briefly rivaling entire galaxies, but the physical mechanism driving them is contested. The leading candidates include the collapse of a massive star into a magnetar, a neutron star spinning at extreme speed with an extraordinarily powerful magnetic field. Another hypothesis invokes tidal disruption, a star being shredded as it passes too close to a black hole, producing a flare as the stellar material is consumed. A third class of explanation involves exotic compact object interactions that do not fit neatly into either category. What the Rubin commissioning data suggested was not just more examples of a known phenomenon. It suggested that the known population of FBOTs was itself dramatically underestimated. The survey depth and cadence of previous instruments had been catching only the brightest and longest-lasting events. The raw frames from Cerro Pachon were showing dimmer, faster events that had simply been invisible to everything that came before. But that was not the most unexpected thing. What caught the attention of a separate group of researchers working on the same commissioning data was something buried not in the transient pipeline, but in the static source catalog. The survey software, when it processes a set of frames, builds a catalog of every point of light it detects that does not appear to move significantly from one night to the next. Stars, galaxies, quasars. These become the reference population against which moving objects are subtracted. But in the process of building that catalog from the commissioning data, the team found sources that were neither moving in the manner of solar system objects, nor behaving photometrically like known classes of distant background sources. They were compact, meaning they looked like points of light rather than extended galaxies. But their colors across multiple filter bands were wrong for stars, wrong for known types of quasars, and wrong for the white dwarf populations that frequently appear in deep survey data. The color mismatch was the clue. Every class of astronomical object has a characteristic color signature when observed across a range of wavelengths. A hot blue star looks different from a cool red dwarf. A quasar, powered by accretion around a supermassive black hole, has a recognizable spectral shape, blue and featureless at certain wavelengths, with broad emission lines at others. White dwarfs cluster in predictable regions of color space. These new sources sat outside all of those clusters. They occupied a region of color magnitude space that existing stellar population models had not populated, which meant either the models were incomplete in a way nobody had recognized, or the sources were something the models did not include. The conservative interpretation is almost always that the models are incomplete, that the outliers represent rare but real objects from known populations, seen in unusual states or at unusual distances. And that interpretation may ultimately prove correct. But what makes the Rubin commissioning data unusual is the number of these anomalous sources relative to the survey area. The density of these objects, per square degree of sky, is higher than existing catalogs of unusual compact sources would predict. If they are rare objects from known populations, there are more of them than anybody thought. And if they are not from known populations, then what they represent is genuinely new. Astronomers working in the field of stellar astrophysics have a phrase for this kind of situation. They call it the color magnitude diagram speaking. The diagram that maps stars and other objects by their brightness and color is one of the oldest tools in astrophysics and one of the most powerful. When a cluster of sources appears in a region of that diagram where nothing is supposed to live, the diagram is trying to say something. The question is how to listen. The tools available for that conversation are spectroscopic. To know what a source truly is, you need to break its light into component wavelengths and read the pattern of absorption and emission lines imprinted by whatever atoms and molecules are present in or around it. Rubin, by design, is a photometric survey instrument. It collects light across broad filter bands rather than spreading it into the fine-grained spectrum a spectrograph would produce. This is a deliberate engineering choice that allows the survey speed and depth needed to cover the sky on the timescale the mission requires. But it means that when the commissioning data throws up a population of anomalous sources, the definitive follow-up must come from other instruments. Spectroscopy on large telescopes. Coordinated observations from the Very Large Telescope in Chile, from Keck in Hawaii, from the upcoming instruments attached to the extremely large telescope currently under construction on a neighboring peak in the same Andes range. That follow-up process was already underway by early 2026. Preliminary spectroscopic observations of a subset of the anomalous compact sources were being gathered and analyzed. The results, as of the time this script was written, had not been published in peer-reviewed form. What the researchers involved in that work have said publicly is measured, as scientific language tends to be under those conditions. The sources do not appear to match existing spectroscopic templates cleanly. The follow-up observations have produced spectra that require careful modeling before any classification can be made with confidence. That sentence, precise and restrained as it is, carries weight. When a team of professional astronomers examining some of the deepest, widest field data ever gathered from a single observing campaign looks at the spectra of a population of unclassified sources and reports that careful modeling is required before classification can be made, what they are describing is the edge of the map, not in the poetic sense. in the literal scientific one, the place where what is known stops and what is being figured out begins. The raw images from Cerro Pachon are doing what great instruments always do. They are not simply confirming the universe astronomers already understood. They are returning data that fits imperfectly into existing frameworks and demanding that the frameworks be revised or replaced. That is how astrophysics actually advances. Not through elegant verification of existing theory, but through the stubborn refusal of new data to behave exactly as expected. There is a precedent for this. When the first systematic photometric surveys of distant Type 1, a supernovae, returned data in the late 1990s, the results were anomalous. The supernovae were dimmer than they should have been at their measured distances. The straightforward interpretation that the universe's expansion was slowing under the gravitational pull of its own matter predicted they would be brighter. The mismatch was uncomfortable for months. Then it became foundational. The dark energy that those anomalous brightness measurements implied now accounts for roughly 68% of the total energy content of the universe in the current standard model of cosmology, a number that was not in anyone's equations before a survey camera returned data that did not match what it was supposed to find. Vera Rubin herself understood this process better than most. Her measurements of galactic rotation curves in the 1970s were anomalous relative to the predictions of the visible matter distribution. The stars at the outer edges of galaxies were moving too fast. The standard gravitational theory of the time, applied to the visible mass, could not account for their velocities. The comfortable interpretation was instrumental error or some misunderstanding of the geometry. The true interpretation, confirmed by decades of independent evidence that followed, was that the galaxies were embedded in massive halos of invisible matter that the instruments of the 1970s could not detect directly. Only its gravitational signature was visible. Only the way it made things move revealed it was there. The observatory that carries her name is now operating in the same tradition, finding things that do not fit, generating anomalies that demand explanation, returning raw images from a mountain in the Andes that contain populations of objects, behaviors, and events that existing catalogs and models did not predict at the observed rates and in the observed configurations. The official legacy survey of space and time has not even formally begun. The commissioning data alone has already produced more than 11,000 previously uncatalogued solar system objects, multiple populations of anomalous transients potentially redefining the frequency of rare energetic events, compact sources in regions of color magnitude space that existing stellar population models do not populate, and spectra that require careful modeling before any classification can be made. That is the preliminary result. That is what the warm-up produced. Over the next decade, this instrument will image the entire available southern sky every 3 nights. It will accumulate more data than every telescope in history combined. And every night that the sky is clear over Cerro Pachon, and the camera cycles through its filters and the alerts broadcast outward to the global network of follow-up instruments, the universe will have another opportunity to show us something else that does not fit. Something else that the best models built from the best previous data failed to anticipate. The history of astronomy is not a story about confirming what we already believed. It is a story about instruments powerful enough to return images that break what we thought we knew. And the most powerful imaging instrument humanity has ever pointed at the sky is just now opening its eyes. What it sees next is not yet in any textbook. It may not fit in the ones we already have. And that, precisely that, is why it matters. Because science does not advance by finding what it expected. It advances by returning, night after night, to a universe that is under no obligation to be simple, under no obligation to be familiar, and under no obligation to stop surprising the people patient enough to look. The raw images are still coming in, and somewhere inside them right now, something is waiting to be understood that will change the picture. The only question is which night's data will be the one that holds it. Stay with this story, the answer is coming.